So thank you guys, and I'm Chen. I'm from Baidu Intelligent Operations teams. So today I'm going to talk about our work on performing service diagnosis. When I first work on the service diagnosis, I asked people what I should output, and they told me that I should output the root cause, the changes of the programs and the data that causes the service faults. And when I work on it for a while, I find that I cannot output that because I do not have enough evidence to correlate the phenomenon to the updates. So I try to set my step back and set a smaller goal. And the goal is to narrow down the checking scope of the faulty service to a module that the root cause belongs to. And it turns out this is still very useful because our on-call engineer can choose appropriate stop-loss actions based on this information. And also our development engineers can also try to study this module to understand what is going on in the system during the time of the faulty things. So today I'm going to introduce my work on automatic matrix screening. And this algorithm can reduce the diagnosis time by 80%, and it only requires a minimum manual configuration efforts. So when I first started on this project, I take a few conversations with our on-call engineers to learn how they diagnose the service. And it turns out that they first perceive the service fault by a lot of PV loss on the front-end modules. And then they will get out a call graph of the whole service. For example, it's shown on the right side. Suppose that module A is the front-end module, and he first will put the suspicion on this module and then check the modules that A directly depends on. So here in this service, it only depends on a single module, that is B. He checked B's status by examining a few metrics on it, and if this B is regarded as an abnormal one, he will move the suspicion to B, and so on. And this procedure is ended when a module cannot move the suspicion downward further. For example, here, G is the root cause module at the end because it does not have any directly dependent modules. So he will mark G as the root cause module. Of course, if G is normal, then E will become the root cause module because all the directly dependent modules of E are normal. So this is just the overall procedure of their diagnosis work. So a straightforward approach to optimize this procedure is to build a diagnosis tool. This tool will show the call graph of the whole system. And then we try to mark the abnormal modules with different colors automatically. So the problem is that how do we mark these abnormal modules? And first, we need the engineers to specify several golden metrics. For example, they find that the response time is a very good golden metric. And then we can collect a set of historic data from these metrics. And in this histogram, we will display the response time here. The gray bars actually shows the expected response time for each module according to their past historic data. And the other colorful bars actually displays the difference between the expected response time and the current observed response time. And the green one means that the observed response time is lower than the expected time, and the other time, the yellow time means that the current time is larger than the expected time. And if the current time actually exceeds a specific threshold, it will be marked as red. So actually, the threshold are also trained from the past data. And from this, we find that different modules actually have different threshold. So some of them, the diff are higher, but they are still yellow. And when we use this tool, we find that many of our engineers actually just do not use the call graph. They can use this histogram directly because the color actually gives recommendation to them. So it means that recommendation is very important. Besides of this observation, we also find that there are several other limitations of this semi-automatic approach. First of all is that we need to synchronize the call graph from the real system from time to time. This is because the system is evolving, so the call graph is actually evolves. If all the systems actually use a standard RPC remote procedural call middleware, we can just perform data mining on the log of this middleware to get the call graph. But unfortunately, many of our product systems have legacy code, so they can use different middlewares. So we cannot actually find a good method to expand our tool. The second one is that the golden metrics must be maintained manually because the newly appeared fault time usually requires new metrics. And the third one is that actually people still need to look at multiple call graphs even for a single product. This is because many of our faults are actually happens inside a one data center. So they have to look at the call graph for each different data center in order to find out which module is the root cause. So this motivates us to build an automatic metric scaling tool. And first, we want this tool to remove the hard dependency on the golden metrics. This means that the algorithm must be able to check all modules and all metrics automatically. And second, we want this, because all these metrics are very different in their nature, so we also want the algorithm to be flexible enough to fit into every different metric. And third, we want to recommend the most probable module to users. This means that the measurement must be quantitative, and also the result must be able to must be easy to read for the engineers to understand what is going on. So we start from the instance level metrics here. So this is our overall procedure to the algorithm. First, we will collect a bunch of the instance level metrics, and then we perform anomaly measurements. The anomaly measurement will transform the metrics into the anomaly scores. And then we will group these anomaly scores based on the instances that they belong to. And then we transform each instance into a measurement vector. And then we can perform clustering on this measurement vector to produce a digest. A digest actually contains a set of instances. All these instances should be abnormal, and also we will also have the related abnormal metrics in this digest. And at last, we will rank this digest, and hopefully we will rank the root cause digest to the top one. So here is the detail. For the anomaly measurement, we focus on the sudden changes. The sudden change actually is the sudden rise or sudden drop on specific metrics. And we choose this because a lot of the faults actually can be able to reflect on sudden changes on certain metrics. So the coverage is quite good. And secondly, we find that these sudden changes, when we show the result to the users, to the engineers, they are easy to understand what is going on inside the system. So, and the last is that sudden changes are easy to detect in our algorithm. We only need to compare the data after the faults and against the data before the faults. So we will collect the data. Suppose we collect some data before the faults. Here we set, we collect the data in a 60-minute window before the fault happens. And also we collect data from 5 minutes after the fault. The reason that the window length of the after the fault is shorter is because that this window length will be counted in the persistence time of the fault. So if this window is too long, and we will experience more loss. So this should be shorter. And it seems that in our experience, 5 minutes seems to be a sweet spot. And then we need to find a way to actually measure this anomaly. And we take the idea of a conditional probability here. The idea is that we want to compute this probability that given xi points, which is the data before the fault, what is the probability that we observe the yj points? Yj points refers to the data after the faults. So we can think about this probability in this way. Suppose there is a random variable here, and it has an unknown distribution. But we know that the xi points are samples drawn from this unknown example distribution. So we try to evaluate every single point of the yj to decide whether they are too large or too small. Here we can define two probabilities. The overflow probability actually measures the probability that the random variable y is larger than the single point yj. If this probability is very small, this means that yj is too large, right? So this refers to a sudden increase of the overall of the curve. And if the underflow probability is very small, this means that the yj is too small. So this refers to a sudden drop on the metric. So the problem becomes that how do we estimate the unknown probability distribution of the random variable y? And we use kernel density estimation to estimate these probabilities. And kernel density estimation actually is a method to estimate the probability of an unknown variable using a set of smaller known probability distributions. In its standard form, it uses Gaussian distribution as its kernel distribution. So suppose we have n xi points. We will create n smaller distributions using these ones. And for each Gaussian distribution, the mean will be the xi points value. And also its standard deviation will be a factor times the standard deviation of the whole xi points set. You can refer to Wikipedia to know what is the exact factor here. And then we can add this together, add this smaller kernel distribution together and compute their average. The average becomes the probability distribution of the random variable y. And then the two overflow probability and underflow probability can be computed by performing appropriate integrals. To deal with different natures of the metrics, we also try to use other kernels. For example, we use Poisson distribution as the kernel to handle the metrics such as the number of packets received or sent per second. And we also use the beta distribution as the kernel to handle the metrics such as CPU utilization or CPU idle, because all these metrics are just falls between 0 and 1, and beta distribution is just fit for this scenario. And then now we have a single point distributions, and then we need to compute the overall distribution, the probability using the single point probabilities. And what we do is just compute the geometric average of all these single point probabilities. This is because we just make a very simple assumption that all the yi points are drawn from the distribution independently. So their joint probability will be their or will be the multiplier of their probabilities. And then we use a average because different metrics will have different number of the y points. This is because they are collected with different cycles. Some of the metrics actually collected every minute, but the others will collect it, for example, in an interval of 30 seconds or 10 seconds. So the difference of these counts will make the multiply results different. So we just use a average. A common practice in the probability is to use the log probability. So if we use the log probability, the average will become an arithmetic probability. And based on this, we can transform each metric into an anomaly score. So the anomaly score is actually the minus log probability, and then we can group them into a measurement vector. So because this measurement score is comparable among different metrics and also among different instances, so we can just use them to cluster the results. We actually cluster the instance within a module and in the same data center. You can use different distance functions as you like, but we recommend you to use the dbScan algorithm to perform the clustering. The result, this is because that we do not know how many clusters to produce in advance. So DBScan do not need us to specify that. And also, there is always some kind of dirty data inside. So DBScan can automatically just prune out those dirty data. And the result is a digest, a set of digests. Each digest contains a set of instances as well as their abnormal matrix set. And at last, we will rank this digest. By ranking, we just consider 3 factors. The first one is that the proportion of the instances in the digest comparing to the total instance in the module. And second one is the number of abnormal matrix. And the third one is the anomaly degree, which is represented by the anomaly score. So if all these 3 factors are large, it means that the impact will be larger. So we will likely to rank the digest higher. So we will just need to check a ranker here. And the right side is example output. The table contains 4 columns. The first column is just the module name. The second column is the portion. The third column is the instance list. And the last column is just the metric list. So we can see that the G module is ranked at the top because it covers 30% of the instances. And from the metrics, we can see that actually G module is overloaded. And the second one is E module. And this is also reasonable because E module directly depends on G module. So when G is overloaded, its response time will be larger. So E will have to make more connections and more calls to G in order to preserve a relatively higher overall throughput. So we try to use a set of historic cases to evaluate our results. And the evaluation is just use the Linux standard system performance indicators. And secondly, those 70 historic cases are just all the root cause of these 70 historic cases can reflect on the Linux indicators. And our result shows that 60 of these cases, we can rank the root cause digest as top 1. So the top 1 precision is over 80%. And we also examine the diagnosis time. The human diagnosis time of these 70 historic cases ranges from 6 minutes to more than 2 hours. And the mean time is just 35 minutes. And our algorithm execution time is less than 6 minutes. So in this talk, I just give a brief introduction of our work on the service diagnosis. And I think that's all for my talk.
All right, anybody questions? No? Okay, then thank you very much. Another round of applause.